Good afternoon. Here are yet again for another lovely session of CENG 3325 Structural Analysis. This will be the 27th lecture in the video series, and this afternoon we are going to look at applying the force method to solve systems of both trusses and frames. So part 1 is going to look at applying the force method to trusses, and part 2 is going to look at applying the force method to frames. So let us review, first of all, I just would like to review briefly some characteristics of the force method. So let us review the basic process of the force method. So I'd like to consider the steps in the force method, and as we discussed previously, the force method can be used as a method of solving statically indeterminate structures. So the first step in the force method will be to determine the degree of indeterminacy, or find the degree of indeterminacy in your structure. So find the degree of indeterminacy in your structure and select an equivalent or an equal number of redundant forces. An equal number of redundant forces. So if we have for example, if we have 4 reaction forces or 4 support forces, then maybe you would have 1 redundant, depending on the nature of the frame itself. For example, on a beam, at least, that would be the case. So if I have a degree of indeterminacy of 1, then I would want to select 1 redundant force. And you often have to be careful to select ones that actually will give you meaningful information. And so see some of the previous videos for strategies in selecting your redundant force. Second, I am going to analyze the structure. We want to analyze the structure with real loads present, but redundant reactions removed. So I want the real loads to be present, but the redundant reactions to be removed. So in the case of, say, a beam, if we had let's say we had a redundant force at point A. If you remember previously in our discussion of beams, it was very common to have like a delta A naught, and that would be the real deformation or the deformation under the real loads at joint A, and joint A would be the location of the redundant. Then, secondly, I will analyze the structure with real loads removed, but a unit load with unit load applied at the location of the redundant. At location of redundant. At the location of the redundant. And I might calculate something like a lowercase delta AA. A delta AA, that would be the deformation at point A under a unit load at A, or the deformation at A, or the displacement at A from a unit load applied at A. And again, you could use whatever method of analysis that you'd like for this, whether integration, virtual work, whatever it may be, to find these. Once you have these, we will do the step that I refer to as balancing deformation. So balance deformation, and if you do know the deformation is equal to 0, you might have an equation like this: delta A naught plus, let's say you had a reaction in the y direction, times a force AY times the unit deformation AA. This being then equal to 0. Although we looked at different permutations of this, if you have multiple redundants, then you'd have like a delta AB, a delta BA, and you'd have to solve a system of unknowns, a system of equations. And we also saw variants where where this is not equal to 0. So for example, in the pure settlement example, I said for one particular joint, that joint was settling 2 inches, so this was actually equal to 2 inches. But anyway, so when you balance deformation, you will solve for the value of the redundant reaction. Solve for their value of the redundant reaction. of redundant reaction. So in this case, you'd solve for AY. So you'd have AY equals some number. And then finally, the last step is just to solve the now statically, solve/analyze the now statically determinate structure. The now statically determinate structure. So for example, if you had only one redundant, once I have replaced, once I have removed the redundant and solved for its value, I can now go and reapply this as a known force. And so instead of having a structure with, say, 3 reaction forces or 4 reaction forces, I now have a structure with 3 reaction forces and 1 load applied in the direction and location of the redundant force that I removed. And that is the basic method for applying, that is the basic series of steps for applying the force method. So now let us consider how to apply this specifically to trusses. Consider how to apply this to trusses. So let us consider for a moment we have a statically indeterminate truss. And let me show you what something like that might look like. So let's say we have a truss. Now we can have indeterminacy both from internal or external. Let's consider a truss that is indeterminate due to external supports. So let's say we have something like this. Maybe a truss like this. Like this here. And let's give this 2 pin supports. Now in certain cases this wouldn't be a problem. So for example, if we had no horizontal loading, we could just ignore the horizontal support at one of these points and treat it like a pin roller support. But let me make this nice and hard and say that there is a force P at a certain angle theta. So let's say there's a certain force P at a certain angle theta. And let's say we have reactions AX, AY, BX, and BY. BX and BY. Oh, cut those backwards. BY and BX. Now the difficulty of this is going to be that you cannot simply ignore the horizontal forces because this reaction, or sorry, this applied force has both a vertical and a horizontal component. So we cannot just easily eliminate one of these right off the bat. We have a truss that is truly indeterminate to the first degree, and this is not going to be so trivial to solve. So we need to apply the force method in order to, or other method, but we could apply the force method to this in order to make this a determinate truss again. So let's consider how to do that. Well, the first step, of course, is going to be to select a redundant. Now, you can choose really any of these forces as a redundant, but when I'm picking redundants when I'm using the force method, I like to be lazy. I always try to pick the laziest solution, and I am so used to seeing, in simple statics problems and things like that, I am so used to seeing trusses that are just simply supported like this with a pin on the left and a roller on the right. And so, you know, I've worked with those a billion times. So I think if I'm going to have a problem like this, I'm just going to immediately select BX as the redundant. Of course, you could pick any that you would like, but you know, if I'm comfortable with working through that, why not just pick something that makes it nice and simple? So just like when I'm working with beams, I love if there's a way to make that a simply supported beam, because that's the nicest, friendliest beam you could ever work with. And so if I go and remove the BX, I get a nice pin roller support and I get a simply supported truss. So I think I'm going to do that. So for my example here, I will maybe select, I could select BX as redundant. I might select BX as my redundant. So then I would then need to go and analyze the truss with the redundant support removed. So the steps really are exactly the same for trusses and frames as they are for beams. So step 2, analyze truss under real loads with redundant force removed or redundant reaction removed. With redundant reaction removed. So if I consider this truss here, when I remove my BX, I am left with this just simply supported truss. And let me draw this a little bit larger here. So let's draw that a little bit larger. Or actually more like this here, because I want to be able to show the deflected shape. And so we have something like this. Here. And this isn't a numeric example, I'm just walking through the general process. And it is going to be under this load P. So under this load P and some angle theta, so I would need to find a px and a py. This thing is going to move a certain distance to the right. This joint B here is going to end up somewhere over here, and so I would get some sort of deflected shape, maybe exaggerated like this. Something kind of like this. Joint B is not going to move down, but it will sort of stretch everything out. But again, this is a greatly exaggerated deformation, of course. So this is joint B here, and I would have a deformation here of, say, delta B naught. This is the deformation. And you know what, I might even put an X there, B naught X, to indicate this is a deformation in the X direction. And that would be important in case I needed to do maybe 2 virtual loads on one joint. So delta box, for example, delta B naught X, would be the deflection of B in X direction under the real loads. Under real loads. So how can I find this? How can I find this deformation? Well, look at this. How can I do that? Well, it's very simple. So, now not necessarily simple to work through, it might be a bit time consuming, but it's not conceptually difficult. If I have my AX, my AY, and my BY, this is simply a statically determinate truss. All I'm doing is asking, okay, I have a statically determinate truss, what is the deformation under a certain load? And how can I get that? Well, we've looked at it many times before, and that is virtual work. This is why I always teach virtual work before I teach the force method, because it can be useful, especially for solving statically indeterminate trusses and frames. So I would use the virtual work method to find the deformation of point B. So you'd use those formulas that we previously derived in some lectures a week or two back, maybe 2 or 3 weeks back, discussing how to apply the deformation of members, deformation of truss members, looking at the internal work versus the external work. You use those to find the change in position of joint B. And once this is able to move, you turn this pin support here into a roller support, this thing will just freely deform under force P, and you can just calculate that deformation just like you would any virtual work problem. So you have that. Then step 3, you would analyze the truss under a virtual load. Analyze the truss under a virtual load. And so what I'm going to do is I will apply a unit load at the joint and in direction of the at the joint and in the direction of the removed redundant, or just in the direction of the redundant support. Of the redundant support. So when I apply, so for example here, I'm going to apply a 1 kip load in the x direction at joint B. Well, I could say it's just a 1 unit load, or just a unit load, without units or any knowledge about the actual object itself, or without any knowledge about the members or anything like that. I don't really know what unit system I'm working in for this problem. I'm just talking very generically. But I would apply a unit load. If I was working with KSI, I would apply if I was working with kips per square inch for material strength, I would apply a unit of 1 kips. If I was working with megapascals for my modulus elasticity, I might apply a unit of meganewtons, whatever it might be. You just use whatever unit is. Whatever unit load is compatible with your unit system. So I would apply a unit load here, and I'm just going to do the exact same thing. So again, apply a unit load, and I will analyze truss under unit load without the real loads present. Under unit load, but without real loads present. So I would have reactions AY and AX, and then I'd also have reaction BY here. And I would get some deformed shape that would look very similar, although just for consistency, maybe I'll show this as being much less deformed. And so maybe then I have something kind of like this, maybe like this. And I'm just sketching this, something kind of like this, whatever the actual deformed shape might be. So, but it would definitely be to the right at joint B. That's what matters. And so, so I need to calculate a particular displacement, and that displacement here, since I have only 1 degree of indeterminacy and only 1 redundant force here, I don't need to have the whole array of subscripts that I would with working with multiple degrees of indeterminacy. So I would just go ahead and label this, say, delta BB. That would be the delta BB here, using the terminology that we looked at previously. Lowercase delta BB would be the deformation at joint B due to a unit load applied at B. And how do I get this? I actually do want to calculate the numerical value for this. Well, you guessed it, apply virtual work. Apply virtual work to obtain our delta BB. Obtain delta BB, and we will obtain a numerical value for that. So again, you can apply virtual work. You have a statically determinate truss here. You just have three unknown reactions. You have 1 simple load. It's not difficult to apply virtual work to this problem. And then let's see, step 4 is just going to be to balance deflections or balance deformations. And it could be done as simply as this. So you might have delta B naught plus lowercase delta BB times BX. And all of this would equal 0. So again, delta B naught states this is how much the truss would move to the right if the restraint at if the horizontal restraint at B were removed. Delta BB says, okay, well, if I apply a unit load at B without the real loads present, how is this thing going to move? And I know that this must equal essentially the negative of this times the reaction force. Whatever that real reaction force is, you can very easily solve for BX algebraically. Or very simply just calculate BX by saying this is equal to negative delta B naught over delta BB. Of course, if you do have multiple redundants, then you'll need to use the same kind of method that we've looked at for beams of multiple degrees of indeterminacy. So, for example, if you had a frame with 2 fixed supports or something, you'd need to look at that a little bit more complex. You need to look at that at a bit more complex level, but all that would just involve is more redundance. Now, once you have that, you simply analyze the now statically determinate truss. Analyze the now statically determinate truss. And calculate whatever terms you need. whatever quantity is desired. So for example, if you're looking for forces, like internal forces in members, you could simply use method of joints, method of sections from statics, method of joints or sections. And if you're looking for something like deformation, if you're looking for deformations, displacements, rotations, here you could use virtual work again. So just like in the case of the beams, where I ended up doing, say working through the equations of deflection multiple times, working through those integrations multiple times, you may have to do the same thing when working through trusses here. So if I give you a truss like this and ask you to find the displacement at this joint, when it's statically indeterminate, you may actually have to work through 3 different levels of the virtual work method. Once to find the deflection under with the redundant removed under the real loads, a second time to find the deformation at B under a unit load at B, and then once this truss is fully determinate, because you've replaced this bx with a known number, you might have to do a 3rd level of virtual work to say find the displacement at joint whatever joint C or whatever joint that is. Okay, and really that is the method of virtual work for trusses. I could go into this longer, I could go into this more detail, but really this is it. If I have time, I may later work through an example of this numerically, but really this is all there is to it for the process of finding, for applying the force method to indeterminate trusses. All right, that'll do it for now. Thank you for watching. Hope you all found this a little bit illuminating. Hope you all enjoyed this. I'll see you all next time, and I'll actually see you fairly quickly for part 2 of this. But until then, I'll see you later, and as always, thank you.